Alrighty. So today we're going to look at a couple of very, very major ways of doing series that are completely unrelated to everything we did last day. There's a very clear line in the sand that separates. And one of the good things is the stuff we're learning today, nothing we did last day applies. And the stuff we did last day, nothing we do today applies. They're completely separate in the types of problems we're going to solve. A lot of the things we're going to do today involve factorials. That's one of the big creatures. But you can't integrate or differentiate a factorial, and you can't compare factorials. So I want to remind people, okay, we've done a little bit with factorials, but not really much. All right. What does this mean? Remember?
Every number of n times itself. Yeah.
Let's say n is large. So first rule is n has to be a positive integer, and then it's the product of all the numbers going down to 1. Okay, to remind us, that's what it is. So you need to get out your calculators for a moment just to make sure we all understand. I'm reviewing this. I know everybody's seen this. I know everybody's seen this multiple times, but this is going to be a major thing for the next couple days. So if I said 5 factorial, that's 5 times 4 times 3 times 2 times 1. What is that on your calculator? Real fast. 120. So, 10 factorial. That's not very big. What's that? All of a sudden, it will feel big. 128?
800.
Wow. Okay. How about 69 factorial? Now, all of a sudden, you're going to get a scientific notation answer because you usually only have about 11 digits on your screen. You're going to get something on the order of, and I'll put a squiggle because I'm not writing any of the digits down. It's going to be on the order of what?
1.7 times 10 to the 98.
Woo! That's a big number. Now, one of the most important things about factorials, and we're going to be using this fact over and over again, is it true that 5 factorial equals 5 times 4 factorial? Is that a true statement?
Yes.
And in fact, could I say that's 5 times 4 times 3 factorial? Yeah. So if I want 70 factorial, that's just 70 times 69 factorial, which should be about, well, 70 times this is about 120. So that should be about 120 times 10 to the 98th, or 1.2 times 10 to the 100th. So when you do that on your calculator, what does it say? Everyone do that one on your calculator.
How did you get that from?
How did I get?
Oh, 69 times.
Because we already have 69 up there, so. So what do you get on your calculator? Do you get about 1.2 times 10 to the 100th, or do you get something else?
I get an overflow.
What? Error? Yeah. Now,
Yeah.
I have a TI-89 titanium. I can go up to 449 factorial before it craps out. Why did it say overflow error?
Because we went over 100 powers.
Yeah, most of your calculators go up to 10 to the 99th, and that's it. Mine goes up to 10 to the 999th, which is reached in 449 factorial. Now, factorials, I use positive integers. Positive integers can get really big, right? I mean,
Right.
On your way to infinity. To say the limit of human technology is a few hundred factorial, that's kind of a problem, isn't it? Because what if I needed 1,000 or 1,000,000? Look, there's no technology that exists. This is Star Wars technology that doesn't exist. And by the way, we will never bother because it just takes up way too much time in storage, so we have tricks. But factorials grow so fast that our calculators can't even keep up with them. So what do we do with them? Well, we do some basic manipulation. Now, I've mentioned this more than once, that I taught the math portion of the GRE test over at San Diego State for a few years. Right before the pandemic, I stopped doing it. I was kind of burned out. I enjoyed it, but it was a lot because, 2 Saturdays are math, 2 Saturdays are English, and I would do about every 2 months. I'd have a new session. Huge class. GRE is the test for grad school. So it's like your SATs for college. Everybody takes the GRE to go to grad school. And the math portion is actually pretty simple. It's geometry, algebra, and statistics. And the algebra, most people were fine. The statistics, I would review mean, median, mode, permutations, combinations, what they needed, and the geometry was the tougher one because of all the vocab, and no one had had it since they were 15. At least the other ones they might have had in college. But I would remind people, when you're taking the GRE, how many of you here have ever taken any form of a math test on a computer? Like the way it used to be with Mesa, you went down to admissions and you actually had to take a placement test. They stopped doing that a few years ago. You could have a PhD in mathematics, and when they give you the placement test, the placement test was to put you in pre-elementary or intermediate algebra. So if you got perfect on the placement test, then you're going to go into intermediate algebra. Regardless of your level of math, it only placed you one of the three. So then you had to say, I'm a calculus person, or I'm a higher. Then you'd have to go through the department and do all this. But everybody took this placement test, and the computer screen had a little calculator on the screen. You guys know what I'm talking about?
Yep.
And that calculator added, subtracted, multiplied, and divided with no order of operations.
Right.
Well, that's the same calculator you have for the GRE. And so I know we've talked about stuff like this before, but you have this problem on the GRE. And you have a calculator that doesn't have a factorial key, and even if it did, 100 factorials beyond what you guys could do anyway, yet this is a standard GRE question, 100 factorial over 98 factorial. This is the sort of stuff we're going to be doing today. See, is it true that I could do this? Is that true on top?
Yes.
And that's how I answer the question. You cancel factorials. So if you had a calculator that didn't have permutation and combination keys, you can still do it. You just have to expand your factorials. And that's one of the key things we're going to learn today is the correct way to expand factorials in general. So what if I had something of this form? I have n plus 2 factorial over n factorial. This would be a typical kind of problem we're going to do. And so our use of manipulation of factorials becomes critical. There's nothing hard about it. I just have to know what the rules are. So if I were to simplify this, what do you think?
N plus 2.
It's the same question, isn't it?
N plus 2 times n plus 1 times n factorial over n factorial.
Aha. And then I can cancel it. Yep. So the canceling of factorials generally always leads to nice, happy, happy things. Now, question.
No.
I'm seeing some nods, some shakes, and the diagonal wag. I'm not sure.
No.
Are these the same or not the same?
No.
Nope.
Well, if I do 10 factorial, 5 factorial, 2 times 5 factorial is 240. 10 factorial, you just said, was over 3 million.
Right.
So I can't, no, they're not the same. This is the kind of error, though, that we sometimes make. We don't intend to make errors, but we'll make errors like this. These are not the same. They're not even close, actually. This guy here, is astronomical compared to this guy here. You can't factor out of a factorial. So it's sort of a simple rule. AB factorial is not equal to A factorial B factorial. And there's no factoring that could be done with a factorial from that standpoint. But I call it running off terms. I can always do this to make my life a little bit easier when it comes to factorials. And we're going to do more factorial manipulation over the next couple weeks. There's some formulas we will generate that are really, really convenient. Formulas that aren't in any math book, but they will come up in the problems that we're doing, and it makes it fairly simple to do stuff. So, now the big picture for today. I'm going to throw a series at you. Now let's say we're starting at 1. It doesn't matter where we start, but we're going to start at 1. And let's say this series, I'm looking at it and go, the terms are behaving a lot like the terms of a geometric series would behave. And what I mean by behaving is they're tending to do the same thing. Remember last day when we did the limit comparison? When we did the limit comparison and our limit was a scalar, right? Not infinity, not 0, just a simple scalar. Then we said these two series have the same behavior and they're literally acting like multiples of each other. What if, okay, think for geometric for a moment. I'm going to put geometric. What makes something geometric? Remember, it means that the n plus first over the nth term is a constant. That's the definition of a geometric sequence. So the series, I'd be adding up these terms. So if I was doing, a half, a fourth, an eighth, and so on, I'm doing 2, 6, 18, 54, and so on. If consecutive terms always have the same ratio, that means it's geometric in nature. And if the terms are getting smaller, positively or negatively, but they're getting smaller, we know that thing's going to converge, and it was really easy to tell what it converges to. What if I have a series that's not geometric, but is acting in this way? Well, wait a minute, but if this ratio is a constant, then of course it's geometric. No, the ratio is not a constant. But what if? What if the limit of the ratio was constant? Oh. Now think about this for a moment. If the limit of this ratio was a constant, then we can correctly say that our series is asymptotic to exactly this geometric series, whatever that one looks like. And now all I got to do is look at R. Remember, if the absolute value of R is less than 1, it's going to converge, else it's going to diverge. Now think about that for a second. That's not that bad, is it? So let's do a few examples of this. I'll walk you through the process. Let's suppose we have the following series. This is not geometric. That n on top means it's not going to be geometric, right? Because the n's growing and the denominator's growing. But you know, as n gets bigger and bigger and bigger, the changes in the numerator are going to be very small, but the changes in the denominator are going to be very large, aren't they? So if I started writing down the terms, you know, after a while, it would kind of look like they were geometric in a sense. I mean, they're not exactly. Consider the n plus first term and the nth term. First of all, what would the n plus first term be?
1.
That means you're replacing n with n plus 1, so what would that be?
N plus 1, 2 to n plus 1.
So then, if I take this, and I write the limit of this, then I would be doing the limit of what? I'll write it out. Of n plus 1 over 2 to the n plus 1 over n over 2 to the n. Now we'll clean that up in a moment. Now, when will this converge? Only when the absolute value of r is less than 1. But I don't have an absolute value, so this is what we do. And by the way, this isn't in any math book ever written until later. And then every math book ever written will say, oh, all this stuff you were doing before, you got to change it because you were doing it incorrectly. Now here's the correct way of doing things. I really don't like it when math books do this. Every calculus book, I have over 20 calculus books. I've edited many, I've been a reviewer for many. And I say, will you stop giving wrong information and then fixing it later? This has to be an absolute value. Because if your r is a negative number, negative infinity is less than 1, isn't it? And every book written says, as long as r is less than 1, it will converge. That's a lie. Only if the absolute value of r is less than 1. Right? If r is negative 10, it's doing this and diverging without limit. No, the absolute value. There is no book ever written that will actually give the absolute value here, but they will later on in the chapter. They'll say, oh, all of that time you actually were supposed to do absolute value. Now, the nature of the problems we're doing are probably going to be strictly positive right now, so the absolute value will feel redundant today. Next day, we learn about what are called alternating series. Therefore, every series you ever do after today will always have negative terms. In fact, half the terms will be negative. Every series after today will alternate. So if I don't do absolute value, nothing I say will be true. So I need this. Now this value automatically is positive, isn't it? Then I can go like that, because that's going to be positive. So do I have even a chance of having a negative in this statement? No. So it feels redundant, but I want you to get used to it. Because what did I say was the next thing we're going to add to these problems? Do you remember last day I told you? We're going to add variables to these problems. And that's why the absolute value is important, because the variable will change if it's positive or negative. So I'm going to write the absolute value, and then I can ignore it because there's no negatives. Does anything combine or cancel? maybe I should rewrite it like this. Does anything combine or cancel? Anybody?
The 2 on top and the 2 on.
Okay.
and then
So I'm gonna have it n plus 1. What am I gonna have on the bottom?
2.
2n.
2n, good. Everybody cool with that? So that this reduced very nicely. And what is this limit? 1/2. And tell me about 1/2? It's less than 1. Ooh, this is not a geometric series, but it thinks it is. Why? Because as we go down the road, consecutive terms, although consecutive terms don't have a ratio of exactly 1/2, they're pretty darn close to 1/2, and it's approaching 1/2. So after I go a little while, you can't distinguish the difference between this series and the series that was just 1/2 to the end to begin with. Because this is less than 1, we can say that this series, the series converges by what we just did is called the ratio test. This is the single most common test that's going to be used, you're going to find.
And does it converge to 1/2?
No. In fact, the geometric series wouldn't converge to 1/2. The geometric series with an r of 1/2, I have a formula for calculating, remember? All we're trying to do is figure out, does this series act geometric in nature? And if it does, what is the r that we'd be comparing it to? We would be comparing this to a geometric series that had an r of 1/2.
Right.
So the r is converging to 1/2, not the summation.
Gotcha.
I mean, let's just write down the first couple terms. Wouldn't it be 1/2, then 2/4, then 3/8? I've already exceeded 1 at that point. What does this add up to? I have no idea, but I would use a computer and have the computer calculate the first, bazillion terms. That's good enough. Actually, I wouldn't even need to go that far. If I wanted 3 decimal place accuracy and I went out 10 terms, I've already got 3 decimal place accuracy because all the terms would only be adding to the 4th or 5th decimal place at that point. Yeah, that's a powerful thing about convergent series. So even though this wasn't geometric, it kind of had that feel. Let's try another one. What if my series was something like this? Let's say on top I've got 4 to the n, and on the bottom I've got n factorial. Now n factorial we're going to see comes up a lot in series. It's a very common term. We don't know where it's coming from quite yet, but we will see its emergence over time, over the next couple weeks. So, first rule of thumb, if a factorial is involved, the ratio test is the only test that works. There's nothing else that can work. If exponentials are involved, the ratio test will always work, but there's a second test we're going to learn today that will also work on exponentials. But for this, ratio test is a perfect one. We had an exponential in that last one, and the ratio test was beautiful because the exponentials canceled. Exponentials and factorials will always cancel using the ratio test. So, I want the limit as n goes to infinity. Now, what is the n plus first term? That means you're going to replace n with n plus 1.
4n plus 1 over n factorial plus 1?
I'm replacing n with n plus 1.
N plus 1 factorial.
N plus 1 factorial. That does matter. That's not n factorial plus 1.
Okay.
It's not even similar to that. Now, I'm going to divide it by this. Can we save some time?
Multiply by the reciprocal.
Multiply by the reciprocal. Everybody okay with that? So if I multiply it by this, I've just performed the same thing. Save ourselves a step. See, I rewrote it here. Have I actually done any mathematics from that step to this step? No, I just rewrote the problem. Oh, so could I have just started here? Yeah. Just make sure you have the correct, right? Start with the n plus first term, divided by the nth, so multiplied by its reciprocal, because these things will usually look like quotients. Now, I can't cancel anything quite yet. Can you rewrite this one?
N plus one.
How would you rewrite that?
N plus one times n factorial.
Is that correct? Is 10 factorial the same as 10 times 9 factorial, and so on? Yeah. Why would I do that? Because now I have something to cancel. How about on top? Could I rewrite this one as 4 times 4 to the n? One of the reasons you might want to rewrite it, I've found over the years, it doesn't matter how good you are at math, sometimes we can't read our own writing. Here's what I mean. Here's what most people do. Here's what most people do. And there's nothing wrong. They just say, oh, I can cancel the 4, I'm going to cancel with those guys. And that's correct. Therefore, am I ever going to write the 4 on top? No, because I just felt like I canceled the whole thing. I didn't cancel the 4 on top. I canceled the exponents. But the way I wrote it, by the way, most of you will not carry the 4 into the next step if you do this, because it looks like you just crossed it off. So I don't like doing that. I'm lazy. I do not want to have to fix mistakes later, so I go like this. I want to physically see the 4 that's left over. Now, what about the factorials? Can I go like that? What is left? What's left?
All but n plus 1.
On top I have a 4, on the bottom I have an n plus 1, and because that's strictly positive, I can drop the absolute value. What's this one?
0.
0. Is 0 less than 1? Yeah. So therefore, what conclusion would you make?
Converges by the ratio test.
Converges.
Converges by the ratio. How did I get a ratio of 0? Did we make a mistake?
No.
No. It's because n factorial is increasing unfathomably quickly.
Way faster than the exponential. So what's happening is, if I go down the line, the ratio of consecutive terms is always 4 over n plus 1. You just told me that. But if I'm 10 terms out, that means the next term is 4 over 11 times as big. What if I'm 1,000 terms out? Then the next term is 4 over 1,001 times as big. What if I'm a bazillion terms out? Then the next term is 4 over bazillion 1 times as big, meaning the next term is becoming microscopic in comparison because this ratio is approaching 0. That means the next term is getting so much smaller so fast. Now, this series converges. What does it converge to? I have no idea. But I guarantee if you put this on a computer and you went out 10 terms, you probably have several decimal places correct. Because the next term is changing further and further out, is what the whole point is. That's kind of a cool thing. I'm never going to ask you to do these on a computer, although occasionally I will bring it up and do it on the computer and just show you how things will look. That's a couple weeks away when we get to those types of applications. But the ratio test is designed for things of this nature because I can't do anything with that guy otherwise. Okay? Now, let's consider this problem. We already know the answer to this. Agreed? We already know the answer to this one. We know it's a divergent harmonic series. Let's try the ratio test on that, just to see what happens. So the ratio test says I'm going to take the limit as n goes to infinity of what? The n plus first term over the nth term, and what does that equal? That would be n over n plus 1? What do you think? Yes? No? Maybe? Anyone? Go out on a limb here. Nod, shake your head. Yeah. This is the lowest level algebra you're going to do. I'm not joking. The lowest level of algebra you're going to do for the rest of your calculus lives, but you can't afford an error. There's absolutely nothing about any of these problems that will be taxing. The algebra we're using is actually below pre-algebra. It's setting it up is the key. There's never going to be a problem where any part of this is going to be challenging. Can't be, because there's nothing going on here, but I have to set up correctly. What is this limit? 1. Well, wait a minute, it's not less than 1. It equals 1. Huh.
So
Wait, but if I have a geometric series and R is 1, I know that diverges, but this isn't geometric. We're trying to see if it acts geometric. So at worst, 1 is kind of ambiguous. But that series diverged, so maybe 1 means diverge. Maybe. Maybe 1 means diverge, because we got a limit of 1. All right? So just for fun, what if we do this? We know this converges, agreed?
Right.
This is a convergent p-series. Let's do the same thing. So I would have 1 over n plus 1 quantity squared over 1 over n squared. And that simply gives us n squared on top, n plus 1 squared on bottom. I have 2 second-degree polynomials, each with a lead coefficient of 1. You don't have to do anything clever. What's this limit? 1. Houston, we have a problem. I just gave you a divergent series. We did the ratio test and we got 1. Then I just gave you a convergent series. We did the ratio test and we got 1. So 2 things going on. You can't use the ratio test on anything that you would do a limit comparison test on. All p-series, I don't care what the question is, if a p-series is involved, you're always going to get a limit of 1. So 1 means there is no conclusion that can be drawn, first of all, but secondly, it means you did the wrong test. If you're getting a limit of 1, whatever test you performed was the wrong one. This was stuff from last day, wasn't it? Right? P-series. Limit comparison, direct comparison, even integral tests. But those were p-series. So those tests worked on the p-series. Ratio test, if I apply to anything that looks polynomial in nature or quotients of polynomials, you're always going to get 1. Because you're changing n into n plus 1, you're not messing with the coefficients. So everything's always going to give you a 1 in the end, no matter what the question is. So if you're getting 1, there's no conclusion that can be drawn. It basically means you can't use ratio test on that one. Does that make sense? So that's why I do both of these to show you, oh, it wouldn't matter if I converge or diverge. I'm going to get 1 for every question. You can make it as complicated as you want. You're still going to get 1 if it's something that we did last day where a limit comparison, for example, would be the appropriate one. Yikes. Okay, so what did you just say? Convergent harmonic, or excuse me, divergent harmonic series, convergent p-series. If I have things that act like this, I compare them to things like this. But if I have exponentials or factorials, now I use the ratio test. See, there's no limit comparison that I could do with this. Could I compare this to the geometric series 4 to the n? No, because the factorial. So I can't do that. Can I do an integral test on this? No, because you can't integrate a factorial. Factorials are not very friendly to calculus. They're great for algebra stuff. All right?
I have a question.
Yes.
So you said the one on the right can diverges for the p-series?
No, this is a convergent p-series. This is a divergent harmonic series. But in both cases, we got a ratio of 1. That's the whole point. I took one that converged and one that diverged, and both of us gave us the same ratio, which means 1 is bad. Now, when we did the limit comparison last day, was 1 good or bad? The number 1. 1 is great. That means those things acted as like they were the exact same thing. So if one diverged, the other diverged. If one converged, the other converged. In fact, it converged to almost the same number. 1 was an awesome limit to get last day. 1 is the worst possible limit we could get today. That's why I said you always indicate the test. Oh, right? So 1 is a great number. By the way, if you were doing a limit comparison and you got 0, that means there's nothing you wrote in any conceivable way that was correct. Everything you did was completely wrong because you can't get 0 if you're doing a limit comparison. But we just did a ratio test and got 0. That's an awesome conclusion, right? In ratio test, 0 is a great number. That means my terms are getting really small really fast. But in limit comparison, it means I did the test completely wrong because I compared it to the wrong thing. Wow. So the type of test you do is very important. And so the conclusion we get. So let's do a crazy one here. I'm gonna like this one. I'll go with 0 this time. This one looks kind of Kind of scary, right? This one's a bit more complicated. Well, I'm going to take the limit as n approaches infinity. By the way, can I start at 0?
Yeah.
Yeah.
On your calculator, do 0 factorial. What does it say? It says 1.
Wait, what?
0 factorial is 1. And that always throws people. I was reviewing factorials recently in discrete, so you guys have seen this recently. 0 factorial is kind of a quandary. Most people, when they go through all their algebra careers, you're told 0 factorial equals 1. How many knew that coming in today? You know, from ancient history. And it usually is something like, oh, it's defined to be 1, don't worry about it. No, it's actually calculated. Factorials come from something called the gamma function, which my DiffyQ people will be doing in a few weeks. Gamma function is kind of a scary, improper integral. It's got infinities, and it needs integration by parts. It's kind of scary. But the gamma function is what produces the factorial. Factorial is a special case of the gamma function, and you can actually calculate through an integration 0 factorial. And the calculation is 1. Most people are told, oh, it's just defined to be 1, don't question it. No, it's calculated to be 1. But why didn't we do it with the other factorials? Well, factorials always end 3, 2, 1. If factorial ended with 0, then wouldn't all factorials equal 0? Yeah, that wouldn't really make a lot of sense, would it? Factorials end at 1. You can't do a fraction factorial. You can't do a negative number factorial. You can only do positive integers. Those who have had, how many have had statistics? So you've done combinations, you know that kind of stuff. So I want to take all of you out to lunch. How many ways can I do that? 1. And that's to take all of you out to lunch. That's the same as asking, how many ways can I leave all of you behind? You said 1, and that's to leave all of you behind. But in both cases, there's a 0 factorial in the calculation. 0 factorial is part of the formula. And if 0 factorial didn't equal 1, we'd be in trouble. So we see that 0 factorial is literally the number of ways of doing nothing. And there's only one way, and that's to do nothing. If there's 50 people in the room and I said, how many ways can I take one of you to lunch? The answer would be 50. But how many ways can I take none of you to lunch? The answer is 1. And that involves the 0 factorial. So 0 factorial, if you even in statistics, which is really, really low level math, we know how to use that. 0 factorial will come up. It's not going to be our answer because we're going to infinities. But that I'm pointing that out because it does not present a problem. My first term here will be 1 squared over 1. That's not a problem. If it were a problem, I wouldn't start at 0. Okay? So, what is the n plus first term?
N plus 1 factorial, the quantity squared.
Oof. Yeah, parentheses are going to be extremely important here. Over.
2n plus 2 factorial?
Oh, good. Okay. It's 2n plus 1 quantity factorial. Are we okay with that?
Right.
That is not the same as 2n plus 1 factorial, which is a common mistake. I'm replacing n with n plus 1 before I get to the factorial. So that's 2n plus 2 quantity factorial. I'm doing this problem specifically because these types of problems come up a lot, but those types of algebra errors follow them too. We make a lot of algebra errors on these types of problems because we get kind of loose sometimes. So that's the n plus first term. What's the nth term? Well, that. So can I just write this then as the reciprocal right next to it? Yeah. An improper use of parentheses completely changes the answer. It's not actually even a similar problem. Improper use of the parentheses will make all convergent series diverge, it'll make all divergent series converge. It'll take me in a completely different direction. So we're doing this problem very specifically so we don't make mistakes. Now, always when you have a quotient involving factorials, you always want to cancel all the factorials. You can't take a limit that still involves a factorial. So I'm going to be able to cancel, but not yet. So what am I going to do with this guy, do you think?
Times 2n plus 1 times 2n factorial.
Beautiful. Everybody got that? That's what that expands to. And I need to do the expansion like we did at the beginning of the class with 100 factorial over 98 factorial. We expanded it until we could cancel factorials. Now what about the ones on top?
You can factor out n.
Can I write that as n times n factorial?
Yeah.
but it's being squared. Okay, so how about if I just do it again? Would that work?
Yeah.
Rather than writing it to a power, how about if I just write it side by side? Might be easier to see. Does anything cancel?
Yes.
Oh, yes. Have some fun now. Canceling is a plus, right? It's all done. Anything else?
No.
All done. Are there any factorials left?
No.
Are you sure? Gone, gone. What do I have left?
N plus 1 times n plus 1.
All right, so I'll write that as n plus 1 squared. How about on the bottom?
2n plus 2 times 2n plus 1.
By the way, could I cancel an n plus 1 from here to here?
Yep.
Yeah. Do I need to? I can. And many of you will. Why? Because that's, what's this? That's just 2 times n plus 1. So could I go a step further
Doesn't it?
and write this as n plus 1 over 2 times 2n plus 1? Is that legal to do that?
Yeah.
Is it going to change my limit?
No.
So regardless of whether you evaluate here or you evaluate here, what are you getting in either case? First degree over first degree, so I can just look at the coefficients, and what will that be?
1 half.
1/4.
1/4.
2 times 2?
Yeah.
About 1/4. Oh. Wait a minute. This crazy quotient of evil-looking factorials thinks it's a geometric series of just simply 1/4 to the n. I'm not going to get the same sum. But what's happening as I go down the road, consecutive terms are looking more and more and more like 1/4. As n gets really, really, really big, right? Just for fun, put a large number in for n, put 1,000 in for n, and calculate it. Oh, it's going to be ridiculously close to 0.25 on your calculator. Consecutive terms are getting closer and closer and closer to a ratio of 1/4, meaning this is acting like that geometric series. Now remember, geometric series, I have to have a small r, but it also matters what the first term is, right? That figures in. So whatever this adds up to, it's not going to be exactly the same as 1/4 to the n, but it will act like a multiple of that in a sense. So after all is said and done, what was the important thing?
It's less than 1.
Yeah, you throw those bad boys here. Again, it's redundant, they're factorials, they can't be negative. So therefore, this series converges
By the ratio.
by the ratio test. Beautiful. Like that? That's not that bad. Factorials are the one thing that's going to give you a little bit of problems at first because you're not used to manipulating them. And we saw this problem here. This is everything. If I don't write this perfectly, then I won't be able to expand correctly and it will change my final answer. Tell me, what do you think a common mistake is? Well, I'm going to replace n with n plus 1. What do you think? Is that a potential error? I just replaced n with n plus 1. Well, I didn't exactly, but it kind of looks like I almost did. Well, what would be the difference if I did that instead? Then I wouldn't have this term, and this would have been infinite. That kind of changed my conclusion, wouldn't it? Oh, yeah, little things like that. What if I didn't have n plus 1 factorial, but I wrote it as n factorial plus 1? Well, then my denominator would have been infinite, and this would have approached 0. Nothing I wrote would have been correct, but I wouldn't have seen what went wrong. So I've got to get the factorial manipulation perfect. All right? Let's try another one. So I have the sum from n equal 1 to infinity of 3 to the n over n to the 100th power. Now, if I just wrote the first couple terms down, I'd have what? I'd have 3 over 1 plus 3 squared over 2 to the 100th, which is kind of big. It's on the order of 10 to the 30th power, by the way. And then the next term would be 3 cubed over 3 to the 100, which is actually a lot bigger than the other one. And these are getting really, really big. Okay, so obviously this is going to, right? Or is it? No, these are getting really, really small. My God, if I do this on a calculator, my calculator is going to tell me it's 0, by the way. Why will my calculator tell me these terms are 0 after a few terms?
Because it's getting too small.
It's the same as the factorial problem. You're going to have more than 99 zeros after the decimal place. And it can't keep track of it. Have you guys ever done a calculation where you're actually calculating with numbers and then your calculator said 0 at the end? And you didn't make a mistake? Yeah, it's because it was smaller than 10 to the negative 99th power. That's not really hard to do. If I just said, let me take a decimal, a small decimal, and now let me have you raise it to a ridiculously large power, your calculator is going to spit back a 0 because it's too small for it to keep track of. So these numbers are obviously approaching 0 rapidly. But just for fun, let's go ahead and go through the whole process because it's a worthwhile exercise. So I have 3 to the n plus 1 over n plus 1 to the 100th divided by this or times its reciprocal. I'm going to be lazy. Okay. Does anything cancel? Well, I get a cancel in here. So what do I have on top? I have 3 n to the 100th over n plus 1 to the 100th. Now, I'm not in the mood to expand the n plus 1 to the 100th, but it is a 100th degree, correct? And what's the lead coefficient? 1. Oh, is this a hard limit to take or is this an easy limit to take? It's one or the other. Is it hard or is it easy?
It's easy.
It's easy. What's the limit?
3.
And by the way, you can do L'Hopital's rule 100 times, don't. How about just 3? Oh, okay. Wait a minute. 3 is... What? These terms are getting microscopic. What did we just say? This is acting like a geometric series with an R of 3? That's completely absurd. How could that be? Well, that's the first few terms.
I feel like a million is
Yeah.
Put a million in there.
ludicrous.
3 to the million over a million to the 100th power, your calculator would actually give you an overflow error because it'd be way beyond 10 to the 99th power. In other words, I gotta go a little ways, but because that's exponential and that's polynomial, this will pass this. It's gonna take a little while because I used 100 as my exponent, but it will take a little while. Does everybody understand that the numerator, if I said, what does the graph of this look like? Think parabolic in nature, but way faster, but this is exponential. It's gonna take a little while, but one is gonna pass the other. Wow. So I did this on purpose. Isn't this devious? These terms they're getting so small and they're gonna stay microscopic for a really long time. Like Chase said, well, what if I go out 1,000,000 terms? Oh, now they're gonna be asked, at some point, I don't know exactly where it's gonna turn around, but at some point it's gonna turn around and it's gonna go the other direction. Isn't that crazy? Okay. 3 to the 4th power is 81. 3 to the 5th power is 243. Why am I pointing that out? Because if I got to 500 on the end, that would be the equivalent of 243 to the 100th power, whereas your denominator is only, what? I'm saying your denominator is now 500 to the 100th power. So keep going and go another 3. Do you see what I'm saying? If I just say go 3 to a couple powers, oh, it's not very hard to have a 3 to a power that will now exceed whatever that is for the n. I gotta go a little ways, but they're gonna turn around. And so I mentioned this before, it does not matter what's happening early, it only matters what's happening in that direction forever. If I get astronomically large, but I come back to Earth, or in this case, infinitesimally small for a really long time, and then eventually astronomically large. But I can't tell early. That's why I'm always puzzled when people are trying to do limits by plugging in numbers. I'm trying to take a limit to infinity, and let me try plugging in 1, 2, 3, 4. I actually had somebody do this on the recent quiz. There was a limit to infinity, they plugged in 1, 2, 3, and 4, and by the time they plugged in 4, they got, I don't know, something like 7 or 8. And then said, therefore the answer is infinity. I'm kind of wondering at the logic there. If I did a limit problem and I got a 7 or an 8, I'm kind of thinking that's the answer. I don't know how you can justify getting a 7 or an 8 and saying, obviously that's infinite. Or in the other direction, I got a 7 or an 8, oh, obviously that's 0. Or even better, I get a 7 or an 8, obviously that's a D and E. I don't know you can make a conclusion I do know you can't make a conclusion ever by plugging in numbers. You can't even figure out the behavior. Certainly not in this case. So when it comes to ratio test, don't be deceived. Just do the test flat out. Now, what is my conclusion for this problem here?
Divergence.
This one diverges by the ratio test. Does it diverge to infinity?
Yes.
Yeah, it's growing without bound and it's not, there's no negatives. I'm not changing sign. So this actually is getting infinitely large. Diverges is good enough. Understanding the behavior, yes, that eventually, like I said, if you put 1 million in there for n, it's going to be, beyond reckoning. It's going to be so big. It's just going to take a long time to get there. All right. Now we're going to look at a different one that kind of works hand in hand. So what if the nature of my problem is this? I have something in the form, I have a general term there, but my general term is also being raised to a power. So when we talk about a geometric series, we talk about things, where it's r to a power. Now, if you remember, when we did the geometric thing, didn't we always write it sort of in this form? We said the nth term was a1 times r to the n minus 1. That was kind of our general term. And then when we did the summation, because it does matter what the first term is if it's going to converge. So when we're doing summations, we usually kind of think of it like this. If I start at n equal 1, this is often like that. Am I worried about the a1? No, because I can put it out here, can't I? So in other words, this has nothing to do with convergence or divergence. It's only the r. So a lot of times we'll say, let's just put this guy out here. So I have something where I'm raising it to a power. But an is not a constant. An is something. Maybe it's a quotient. Maybe it's a single term. But an is not constant. What if? What if the limit as n goes to infinity of an in absolute value equals a constant? And think about this for a moment. I have something, and what we'll do is several examples. I have just something. I have a quantity being raised to a power. But that quantity is approaching a constant. Then would it be safe to say that this is acting like a geometric series where an is acting like that constant? Yeah. So then all I need to do is have this be less than 1. This is what's called the root test. Or more specifically, people call it the nth root test, which is kind of ironic. Because you're never, some of you will, because you just like making things harder. I'm looking at something of the form, it's approaching r to the nth power. So technically, if I take the nth root of that, it's just the r. Well, you're only looking at the r. You're not taking an nth root, you're just looking at the base. It's generally called the nth root because I have something to the nth power and I just want the base, which is equivalent to saying the nth root. That's kind of overkill. You see where I'm going? You're not going to sit there and physically take roots of things and then come up with something. So let's do a really simple example of this. I have the sum n equal 1 to infinity of 4n minus 3 over, let's say, 3n plus 5, and I'm raising that whole thing to the nth power. Now, just for the heck of it, could we try to use ratio test on this? Because I do have, it is exponential in nature. Could I try the ratio test? Of course I could try the ratio test. Let's see what happens if I do the ratio test. So I would take the limit as n goes to infinity of, now what's the n plus first term? Careful. I'm replacing n with n plus 1. How about, I'll just write it. 4n plus 1 minus 3 over 3n plus 1 plus 5, and all of that is being raised to the n plus 1 power, and then I want all of that over 4n minus 3 over 3n plus 5 to the nth power. Okay, great. Now I'm going to go ahead and expand this, and then I'll flip that over, and I will cancel, except there won't be any common terms, will there?
No.
So I won't be able to cancel. And the exponents aren't going to cancel on top, meaning essentially this is impossible. Can't use the ratio test on this one. I don't have anything to cancel. I don't have any factorials. I don't have any, 2 to the nths. I don't have anything that looks like that. Everything's polynomial-ish. If I flip that up, that's fine, but I'm not going to have any 3n plus 5s. I'm not going to have any 4n minus 3s, and I'm not even going to have a common exponent. Oh gosh. So I can try, but I will fail if I try to use the ratio test on this one. But what if I do that? What if I only look at that piece right there? Let's take the limit as n goes to infinity. Remember, I said it needs to be in this form. So I'm only looking at the an. I'm only looking at the base. I'm not looking at the exponent. Can you do this limit? And again, technically, absolute value. Can you do it?
4 over 3.
It's 4 over 3. Is 4 over 3 good? Is it bad?
It's larger than 1.
It's bigger than 1. Therefore, what? No. It's divert. This is the only test that exists. There is no other test. If you have to use the root test, there is no other test. So it diverges by the root test, or if you said empty root test. Why? Because my base is approaching 4/3, which means my summation is acting like 4/3 raised to a power. But 4/3 raised to a power is a geometric series where the r is too big. Ah, so just for fun, what if I had had the reciprocal of this?
Converge to 3/4.
Then that limit would be 3/4, so we'd say this series is acting like a geometric series with an r of 3/4, therefore it converges. Oh, okay, that's not bad. But in either case, I was not going to be able to use the ratio test. The ratio test only works on exponentials and factorials. Right? We tried it on a p-series earlier and it failed. We saw that. It didn't give us a conclusion. And it's not that it would fail in this case, it's that I actually can't evaluate that limit we just tried to do. When I replace these with n plus 1 and the exponent with n plus 1. Sorry. Thought I had that off. Oops. 1 second. There we go. Turn that buzzer off. So the root test. Now let's go back to a problem we've already done. We did this problem to start the class. Is that correct? Could I use root test on this one? The answer is yes, but I have to be kind of creative in how I rewrite it. In other words, I have to write it in this form. I cannot use root test yet.
1 over 2.
Well, okay, I'll do my part. There. You all agree with that?
Right.
What is the numerator?
1.
If I raise 1 to the nth, I'm not going to get n.
N to the 1 over n?
Yeah, multiple, you guys saw it. N to the 1 over n. Ooh. I don't know that I like that. This is correct. Is that going to be easy to deal with? I don't know. But it's going to come up a lot. So I want to derive a simple formula because I'm going to show you, this is something that will come up a lot and we can take shortcuts. Once we derive a formula, you can always use it forevermore. You don't have to rederive it. You don't have to invent a car today before you go home. Right? You don't have to invent a combustion engine and the wheel. We're still working on that one, and now I can go home. No, it's already been done. You've already got it. Once we prove something, if we use that result again, we don't have to reprove it. I would like to take the limit as n goes to infinity of n to the 1 over n. This one's going to come up really often. Yikes. Oh, well, wait a minute. This doesn't look that different from stuff we've already done. What if I do the e to the log thing? And then, of course, we were doing stuff like this in my DiffyQ class, yeah. And everybody was, they were all getting into it. You guys know what to do, right? Everyone loves making the sound. So if I do this, then I get e to the 1 over n log n. Oh, heck, how about if I just write it log n over n? Well, I haven't bothered writing 1 over n. Now let me pull the e on the outside, because you can't L'Hopital it with the e. But if I write e to the limit, now it's just log n over n. Numerator and denominator both growing without bound. Can I L'Hopital that?
Yes.
Yes. That's exactly what I want to do. This is not a hard L'Hopitals. Oops, sorry. E to the, what am I going to get? 1 over n over, and as n goes to infinity, that approaches 0. Oh, well, that's kind of helpful. N to the 1 over n approaches 1. Now, I have an n. What if that had been an n to a power? Like n cubed or n to the 4th? Then wouldn't I see it right here where the 1 is? So here's what I'd like to do. That's true, but I'm only going to see this expression if I have n to the 1st power. But if I have n to any power, let's say it was n to the kth power, for any version of k, here's what I'd really rather you do. You're going to like this. Same answer? It's going to be 1 for every exponent. Is that important? Yeah, that's a really huge result, and it means you don't have to go through and prove it every time. That's kind of cool. I don't want to have to reprove things in order to use them. So when I go to here, the question was, what is the limit as n goes to infinity of n to the 1 over n over 2? What's the answer? We just did the numerator.
1 over 1.
It's 1/2, which is less than 1. Hey, wait a minute. When we did the ratio test, we started the class with the ratio test. What ratio did we get with the ratio test?
1.
Go way back, like an hour. Didn't we get 1/2? I'm going to give you an absolute mathematical statement. Many, many problems, you can do both ratio or root test. There are many problems. Anything exponential, you can do both, for example. Any problem where you can do both, you will absolutely always get the same result. It would be impossible for you not to get the same. What did you do in ratio test? You said the ratio of consecutive terms is approaching that R. Here we're saying anything of the form, a n to the nth power, this thing is approaching R. It's the same R. It's the R from the geometric series. So the fact that we got 1/2 using the root test and we got 1/2 using the ratio test should not surprise us. I have to get the same thing, because in both cases I'm looking for an R that goes with a geometric series. So which was a simpler problem? This problem or the ratio, or would you say it was pretty even? I think it was pretty even in this case. I don't think it was. Now, if there's a factorial involved, can't do this, because I can't take a factorial and make it something to a power. So factorials are exclusively ratio tests. Exponentials can go either one. But the first problem I did was I had a quantity to a power, so that wasn't even exponential, but that one had to be root because I could write it in a form. So let's keep going. Let's say I've got n to the 3rd over, actually, no, I'm going to put the n to the 3rd on the bottom. What am I thinking? Gosh. 3 to the n over n to the 3rd power. How's that? And we want to do this one using both ratio test and root test, because I want you to see the similarities. This is exactly what I was talking about. The n cubed is a p series, but that's not the important part. That's exponential. That's the dominant thing. So I can use a ratio test because of the exponential. I can use a root test. The thing is, with the root test, you have to be a little bit clever. I have to be able to rewrite the problem. And for that reason, some people will shy away from the root test because they have to rewrite it. But I'll give you a hint. If you rewrite it correctly, the root test is always exactly one step. And in other words, it's a very simple. How much work did I do taking this limit? None. Right? With the ratio test, there's always going to be canceling and rewriting, and not complicated. There's just more algebra. So let's do both. But this time, let's start with the root test. So if I'm going to use the root test, then I need to first rewrite this as something to the nth power. Okay, so 3 on top and what on the bottom?
And to the
N
3 over
squared.
n.
N squared? No.
The 3 over
About 3 over n,
Oh.
right? Because you multiply exponents at that way. Now, if I make a mistake here, it could affect my conclusion. So I've got to be really careful here. As n goes to infinity of 3 over n to the 3 over n, if it helps you, you could think of it like this. Right? The limit of a quotient is the quotient of the limits. Is that true? Now, I'm going to show you another thing here you're going to like it, because a lot of us will say, wait, why can I do the same thing here? Well, is the following statement mathematically valid? The limit of a quantity to a power is the limit to a power. So everything I just said is absolutely valid. I can evaluate the limit right now. But if you're not sure, I can evaluate the limit right now. But if you're still not sure, I definitely can evaluate the limit right now. Because my denominator is approaching 1 to the 3rd power, which is still 1. Everything I just wrote was true and correct. You stop at any point along the way. What do you think my preference is?
First step.
First one. Yeah, the first opportunity you have, as long as you understand that you can. If you're not sure, take it a little further. But you better get what? 3, which is bigger than 1. So this diverges by the root test. Okay? Now let's perform the ratio test. One of the big goals today is to be able to correctly set up and do the algebra for the ratio test. Because as we go further, the ratio test is actually going to be by far the most common test you do. And the reason is actually because when we throw variables in here right here, we're going to throw variables, but it won't be an x. It'll be x to the nth power. It'll always be x raised to a power, which means that the ratio test is the easiest one to use. It could use a root test, but a ratio test will be the easier one to use most of the time. All right, so now we're going to do the ratio test. So I want the limit of consecutive terms. So I'd have 3 to the n plus 1 over n plus 1 cubed divided by the nth term, or times its reciprocal. If I can rewrite this correctly, I just said, if I can write this correctly, that's the limit I was taking, and we all could have evaluated it right here. That's a fairly fast route, but this is the key step. I've done everything correct. Can I evaluate this yet? Nah, I gotta do some canceling. I gotta do some manipulation. Not much, by the way. Probably 1 step. I don't think I can do anything with this. I don't think I can do anything with that. How about the 3's?
Yeah.
3 times 3 to the n.
Numerator and denominator are both 3rd degree. Can I take that limit without doing any work? Yeah, sometimes we forget. Yeah, that's way Calc 1. And I don't say it jokingly when I teach Calc 1. This is day 3 of Calc 1. We do this limit. And we show, because we multiply top and bottom by 1 over n cubed to justify, as long as the degrees are the same, it's the quotient of the lead coefficients. You're looking at the bottom going, but don't I have to expand it? Isn't the coefficient of n cubed going to be positive 1? So no, don't expand it. It's 3 over 1. This was my promise. You have to get the same result. 2 completely different tests, but they were both going after the same thing. They were both going after showing that the original series acts like a geometric series with an R of 3. And a geometric series with an R of 3, we definitely know, diverges. So my conclusion now would be this series diverges by the ratio test. You would never do both tests. That's kind of overkill. You with me so far? Okay. Now, I mentioned last day, we're We're learning tools right now. We're just gathering tools. When you first learned what a derivative was, you learned it was the instantaneous rate of change on a line, right? The tangent line as opposed to the secant line, right? And then we said it's the slope of the tangent line, it's the instantaneous rate of change of y with respect to x. Great. And then that was the only thing you ever used derivative for. No, that was your first introduction to derivative. How about integration? Your first introduction was it was the area under the curve, right? Y equal f of x. Is that the only thing you did with it? I mean, didn't you use it for arc lengths and surface areas and volumes by rotation? I mean, no, that was your first exposure. You learned how to differentiate, and now you know a bazillion applications of the derivative. It's an instantaneous rate of change of something. And by the way, literally after the first day, you've never used it for a tangent line ever again. Why? Because there doesn't have to be a graph involved. When you get to Calc 3, you do derivatives in higher dimensions. There's no lines. It's still the instantaneous rate of change. Same meaning, way broader expansion. You have way more uses for integration. So once we learn to differentiate, we could then start applying it to problems. Once we learn to integrate, we could then start applying it to problems. We're learning how to determine the convergence or divergence of a series. We have no use for it yet. But as soon as we get done with this, which is the next class we finish off every conceivable series that exists that's numerical in nature like these, we'll learn how to determine convergence or divergence. Then we'll start answering questions. Then we'll start throwing variables into the mix and saying, now what questions can we answer? And there are so many answers. There's so many types of problems, but we're establishing, right, the base. I know how to determine convergence or divergence, because if I don't know how to do that, I won't be able to answer the higher level question. You couldn't do a single application of the derivative until you could take derivatives, right? Can't do an application of an integral until you can integrate. You didn't start with the applications. You started with learning the rules and what you could and could not do, but we're kind of doing the same thing here. Now let me take you to sort of a crazy cool one, right? What if let's do something like, let's see, how about we don't like that numerator, do we? Is that exponential? The exponential would be constant to a functional power. Is it polynomial-ish? No, that'd be variable to a constant power. This is variable to a variable power. Remember recently we looked at limits like x to the x, and we don't like that one. That one, why? There are absolutely no rules that apply to function to a functional power. No derivative rules. You had to change, remember, e to the log. You had to do all sorts of clever things. But I'm not integrating. I'm not differentiating. I'm just asking the behavior of this thing. Oh, I could start by writing the first few terms. That'll tell me, right? No, we already see that doesn't work. What tests can I perform on this? Can I do anything else? No, because the factorial. So let's do a ratio test and see where that leads. So I want the limit as n goes to infinity of, this is going to be kind of goofy, n plus 1 to the n plus 1 over n plus 1 factorial divided by the nth term, or simply multiplied by its reciprocal. Wow, this looks very unfriendly. Is anything going to cancel in this problem?
The factorial.
I definitely can cancel the factorials. How about the exponential stuff? That's a little less obvious. What if I do this? Thought I had more colors available. Is that true? Okay. Why did I do that on top? You may see the obvious reason? Little extra cancellation goes a long way, right? Where's my kids like to say, overkill is underrated. Feels like overkill, but it's not. Okay. Now what do I got? On top, what do I have? This. On the bottom, I have this. Well, that's really helpful. They both go to infinity. Can I just do that? No. And that won't help though, because the exponent is not constant. Yeah. In other words, it's not polynomial where I can bring down the exponent and decrease it by 1. That only works if it's a constant. What do you think?
Could you do 2 tests in one problem?
No, but that's scary, but that doesn't look as scary.
You can pull the exponent of n out, and you've got n plus 1 over n, all of that to the
Okay,
power of
okay, I like that suggestion. Chase says, without having any other ideas, how about if I do this? Is that legal? Yeah, it's simple exponent rule. But why the heck would I do something like Is that true? Okay, now what? We're done. And I have said it before, that is considered the single most important limit in existence. That's E. Whoa. Gotta admit, that's kind of cool. We just took the ratio of consecutive terms of something that literally looked impossible, and we got E. Oh, by the way, how big is E?
bigger than 1.
It's bigger than 1. It's hard to see. That means this is acting like a geometric series with an R of E. Therefore, what? This diverges by the ratio test. The numerator is actually quite friendly for the root test. The problem is the denominator. You can't take a root of a factorial. So I can't use the root test on this because of the factorial. Factorials, I love working with factorials because of the canceling effects. Yeah, it's so nice, but factorials from a calculus standpoint are not very friendly. Can't differentiate, can't integrate, can't do certain things. I can only get canceling. But we did cancel all the factorials in the first step. And then we just used a little bit of algebra. If I hadn't done this, that step right there, then I would have still had an n plus 1 on top, and then it would have been really hard to see how to make these work. But by doing that little bit of canceling on top, I could take any variation of this question then. And you guys would now know how to attack it. Does it come up a lot? No. Does it come up? Yes. Now, I want to show you something because today, a major theme of today is factorial manipulation. If you have had statistics, then you have done things with factorials. But if you didn't have statistics recently, you might not remember what you did with factorials, or even where factorials come up. Does anybody know what the use of a factorial is generally?
Combination of
Well, no, that's down the road, just the factorial itself. It's how many, if I have n distinct objects, that's important. If all of you were clones, and you all rearranged yourself, would I even notice? I wouldn't notice. But you're not clones. So if you rearrange yourself, I would notice. So imagine I'm going to have you all stand in a line, one line. How many ways could I have you all stand in line? That's what a factorial is. A factorial is I have n distinct objects. How many ways can I arrange them? N factorial. Permutations and combinations are now further. What if I don't want to arrange all of them? What if I want to pick 5 of you for a basketball team and I'm not putting you in any order? That's combination. But factorial is simply how many ways can I arrange n distinct objects. So I have 10 different books. I want to put them on the shelf. There's 10 factorial ways I can do that. So that's what factorial really, that's the original use. That's the simplest use. Definitely not the only use. And we use a lot. So I want to calculate a large factorial. I have a large factorial. I need a calculation. And let's say my calculator can't do it. Or let's say, I have my TI-89. But I want 1,000 factorial, not 449. I want 1,000,000 factorial. I want 1,000,000,000 factorial. I want a number. Okay, we know that. Don't worry about the size of n right now, but think I want big N. Tell me about the natural log of n factorial. Well, it'd be the natural log of this. What's the log of the product? Think about it. There's an identity. The log of the product is the sum of the logs. Huh. I have a computer. I know how to write a do loop. That's, by the way, the simple, if you've ever done anything with computers, the absolute simplest thing that exists is a do loop, right? From I = 1 to n do. I taught programming for 10 years here. That would literally be on the first day of your first computer class that you've ever had, right? For I = 1 to 1,000,000 do. And the entire program from beginning to end is just a few lines. I want to do 1,000 factorial. So here's what I want. From I = 1 to 1,000 do. Add up log 1, and then the counter would change it to 2, then to 3, then to 4, and it would stop at 1,000. I want you to add up, so imagine n's 1,000. I want you to add these up. Is that going to add up to a huge number, or is it going to be really small? Well, how big is log of 1,000? I mean, we've done stuff like this before. Is log of 1,000 astronomically big? Oh, it's like 6.9. Okay. So if I said add up, go log 1 through log 1,000, add them up, it's going to be actually a very small finite value. Let's say, for lack of a better, let's just give this a name. Let's just call it A. Okay. Can you now tell me what n factorial equals?
E to the power of A.
And that's how you do it in real life. I want 1,000,000 factorial, and I want a number. It would take a computer, I don't know, 1,000,000's a lot. Okay, maybe it would take a whole minute. It's just adding numbers. It might take a whole minute to add up the first 1,000,000. And now my answer is e to that number. That's it. That's how you do calculations larger. Your calculator, when you asked it to do 69 factorial and it gave you an answer really, really fast, do you think it was actually multiplying 69 times 68 times 67 times 60? Maybe. You'd be amazed at how your calculator does calculations. Have you guys ever done calculations where it actually took a few seconds? You had to wait? Because the way your calculator does a calculation is not the way you do a calculation. It's actually quite different. In a lot of cases, it's actually doing the math we're about to do. It's doing series. And as soon as the last decimal place on your screen stops changing, it will give you a number. In some cases, it's a really easy thing. And I'm not talking